We're going to be talking about AI today with a couple of researchers from the T.J. Watson Research Center at IBM Yorktown. And if I can have you introduce yourselves first, and then just talk a little bit about what you're doing. Then we can get into the details.
I'm Mudhakar Srivasta. I'm a distinguished research scientist with the IBM T.J. Watson Research Center in Yorktown Heights. I have a small team of about 10 to 12 people working on distributed AI. The primary focus area under that is spatiotemporal analysis. So basically we analyze patterns over moving objects ranging from people to cars to asteroids to rhinos, and something that we'll talk about in a lot more detail in the next few minutes.
Great.
My name is Raghu Ganti, and I'm part of Mudhakar's team. And we around about 8 years back we started the work on spatiotemporal analytics, and which has now grown into much larger. We have several products, about 12 different IBM products that we have integrated our library with. And we are continuously working on more and more real-time problems as well as AI-related problems on top of spatiotemporal data.
You mentioned asteroids and saving the world. Talk about the scope. So are you dealing with almost anything with geospatial data, or asteroids to rhinos is a big leap?
Yes, so that's a very interesting question in itself. But ultimately, it's the underlying mathematical model that we are working on. So we work on an ellipsoidal Earth mathematical model. So we treat the Earth as an ellipsoid, and we track movement of objects, whether it's cars or rhinos, on this ellipsoidal Earth. It just so happens that asteroids do also take elliptic orbits around the sun. So the same kind of math applies there. Except that in one case we are working on a geocentric coordinate system, we are working on latitude, longitudes.
Yeah.
In the case of asteroids, we work on heliocentric, meaning sun-centric coordinate systems, meaning sun is 0, 0, 0 in some sense.
It's about showcasing that our library is capable of handling not just very, very fast-moving objects bound by physics laws, but also objects that have a mind of their own and they're moving around.
Okay, so there's a commonality in the modeling that you're doing.
Yes.
And I understand there's a lot of machine learning involved. Can you talk just a little bit about that, and then we'll get into the details of one of the examples?
So in the case of, say, protecting rhino from poachers, it's a very interesting machine learning problem. So normally you would approach by tagging the animals. You want to track their animal movement. We can track vibrations that will tell them whether they are moving fast, moving slow. We can have GPS sensors on them that can give us the positional information and so on. But the issue that when we put a tag directly on a rhino is that the radio signals may be triangulated by a poacher. So if you put a tag on a rhino, you might in fact be telling where the rhino is located to somebody whom we are trying to protect the rhino from in the first place. We have to put tags on other non-endangered species which happen to be in the vicinity of rhino. They are sharing the ecosystem with the rhino. In this particular case, we are putting the tags on the impalas, the zebras, the wildebeest. They are denser, they are larger in population. They are in the vicinity of the rhinos. They do tend to respond, behaviorally respond when there is a poacher in the vicinity. So we do indirect sensing, meaning we don't directly tag the rhino, but we tag these other animals, and then we try and infer whether there is a poaching activity that's going to take place in the next few minutes, 5 minutes, 10 minutes, 15 minute kind of a time range.
Because it has to be predictive to be useful.
Yes.
Right?
Yes.
Okay. When you said infer, are you talking about inference in terms of logical reasoning, or in terms of when you take supervised learning and you do the training and then you infer from that? How are you drawing these inferences?
It is about being able to marry some of this very little labeled data with more unsupervised techniques, things like clustering, and being able to identify, what is the right label and how do I train a model with very little data. So that was the main challenge that we faced, and we overcame that by using unsupervised techniques with guidance from the label data. It's just saying that, when a poacher attacks, the animals behave slightly differently from when a predator attacks them. and being able to use that information and create AI models based on that. I think that's sort of the key in coming up with the right AI model in this scenario.
I love the idea that you are modeling this ecosystem, if you will, by directly observing other participants rather than endangering the rhinos as you do it. This is great because it sounds like you're combining or integrating multiple types of machine learning with sensors, what we think of as the IoT, to create a solution to preserve the wildlife. We have rhinos and we have asteroids, so they're maybe the extreme, no disrespect to rhinos, but in terms of speed, when you're talking about geospatial, it sounds like one of the issues is how fast can you react, but I would think that is influenced heavily by how fast the object is moving. Can you give me any other examples between those?
Recent example is about being able to predict the encounters of flying airplanes, especially with the increased volume of the number of airplanes in airspaces. A key challenge and a very difficult problem is for the air traffic control to sort of tell the planes what is the landing patterns, what is the takeoff patterns, and so on. And to assist an air traffic control, we want to be able to provide a predictive model that can tell you, are these two aircrafts going to be where they should not be in the same joint airspace? And that is where I think, last year we developed this new operator for streams that can do in real time, be able to ingest, the volume of data that is coming in, the speed and velocity of which is quite large because you're monitoring these aircraft in millisecond time ranges, to be able to identify and predict if these two aircrafts maintain their current path, they are most likely going to end up in a situation which they should not be in, and alert the air traffic controller to be able to take evasive actions much before they are able to even detect such a thing. So that is another aspect of real-time data and very fast-moving objects, which is not as fast as asteroids, but not as slow as rhinos either. So that's something which
sounds like a really practical application.
Absolutely.
I'm all for saving the rhinos, but I'm also all for saving myself when I'm in the air.
Yes, very much so. Very much so.
Excellent. Well, thanks so much for joining us today.
Sure.
Thank you.